Okay, so I'm going to start with a real quick review of electrochemistry from first year chem on applications of redox and what redox is. So quick review, oxidation reduction, it involves a transfer of electrons. That's a kind of a reaction. People abbreviate it as redox. Okay, reduction, oxidation. And they have to happen in conjunction with each other. But I don't want you to get the idea that every reaction is a redox reaction. If it's acid-base, it's not redox. If it's a precipitation reaction, it's not redox. Single replacement reactions absolutely are redox. Many, maybe most combustion reactions are redox, and most synthesis reactions are redox. And then, of course, any kind of reaction that involves a transfer of electrons is redox. So it is a broad category, but it's not every reaction is redox. A couple of definitions for you. When I was in college, they taught us this little mnemonic trick. Leo the lion goes grr. Leo stands for loss of electrons is oxidation, and gain of electrons is reduction. But you really do have to kind of know what those terms are. You can't always be falling back on the definition. Okay, oxidation, I'm going to say oxidized or reduced a lot. And it is something that just kind of, it has to come to your memory pretty quick. Okay. In order to figure out something's been oxidized or reduced, they talk about things called oxidation numbers, or sometimes they call it oxidation states. What they are is they are assumed charges on each element in a compound or an ion. So it's very similar to something you've done in the past where you guys used to figure out Roman numerals for metals like iron 3 oxide. It's very similar to that. And there are certain rules that are a little bit different than the rules you're used to for Roman numerals. First rule, when you're talking about oxidation numbers, elements in their standard states are 0. If you have something that is a monatomic ion, it's the charge on the ion. So if I gave you Cl1-, its oxidation state is 1-. Okay, so that's a monatomic ion. If you have a compound or a polyatomic ion containing oxygen, oxygen's -2 unless it's a peroxide. I would estimate peroxides are about 10% of the compounds you would ever possibly see. Okay, probably even lower, maybe more like 5%. Okay, it's not very common, and I'll show you what it looks like when you see a peroxide. In a compound or polyatomic ion containing hydrogen, hydrogen's +1, unless it's a metal hydride where the hydrogen's -1, and I would estimate that as less than 1% chance of running into a metal hydride. Okay, really, really small. If you have an alkali metal in a compound, it's +1. And here is kind of a rule that is a little bit maybe different from what you're used to seeing. In a compound, the most electronegative atom gets its most common charge. If there's no way to figure it out from these rules, then this is kind of like the default rule. Okay, and then the final rule, which is the most important one, is the sum of the charges of all the oxidation numbers, if you want to call them that, have to equal 0 if it's a compound, or the charge on the ion. And I'll show you what that looks like. So it's very similar to what you guys are used to doing. So the first thing we're going to do is we're going to identify the oxidation numbers on each element in the following reactions. So aluminum's an element in its standard state, it's 0. Fe is a monatomic ion, +3. This Fe is an element in its standard state, and that Al3+ is a monatomic ion. So those are pretty simple. The way you can identify whether it's been oxidized or reduced, if the oxidation number increases, it has been oxidized. It's lost electrons. Electrons are negative. If the oxidation number goes down, it's been reduced. Electrons are negative, so if it becomes more of a negative number, it's been reduced. It's gained some electrons. Aluminum went from 0 to +3. It has been reduced. The Fe went from 3+ to 0. Sorry, God, I read that wrong. Oxidized, 0 to 3+. It has been oxidized. The Fe3+ went from 3+ to 0. It's been reduced. Okay, I'm going to go through and do this one. The hydrogen in a compound is +1. Now, we don't have a rule for sulfur. Now, I know you can look on a periodic table and say sulfur is -2, but we have to use our rules for oxidation numbers to figure out what it is. So if each of the hydrogens is 2, I'm sorry, 1, and there are 2 of them, they add to whatever the sulfur is to the charge on this compound, which is 0. So sulfur is -2. And then each of the hydrogens is +1, and that's how you refer to it. You don't refer to the total charge, just each one of them. Copper here is an element in its standard state. In here, I don't have a rule for copper, and I don't have a rule for sulfur. So this is where that rule, the most electronegative one, gets its most common charge. So sulfur, according to the periodic table, is more electronegative, and its most common charge is -2. Puts copper at +2, and this at 0. Hydrogen goes from 1 to 0. It has been reduced. The entire compound is referred to being as reduced, but technically it's the hydrogen that changed charge. The sulfur stayed the same. The copper went from 0 to +2. It's been oxidized. Okay. Down here it's a little bit harder. Inside this is a polyatomic ion. It's missing the positive part. It's probably potassium or sodium or something else, maybe hydrogen. And it's a spectator ion. It's not really doing anything. And so what I have is I have a polyatomic ion with a charge of -1. Okay? So to figure this out, the oxygen is -2, but I have 4 of them. So 4 times -2 added to whatever the manganese is, my hand hit it, sorry, equals -1. Okay, doing the math, manganese in this case is +7, and that is the largest value you'll ever see. Over here, manganese is 2, oxygen is 0. Now inside here, hydrogen peroxide. You don't know it's hydrogen peroxide, but I'm telling you it is. It's not water, obviously. Hydrogen is +1, and so this is how you can kind of recognize a peroxide. If it was oxygen, then there wouldn't be 2 of them. If it was -2 charge. Since there are 2 of them, whatever their charge is has to add up to 0, so it has to be -1. That's how you kind of can tell, because H2O2. It's like that. Peroxide is technically this ion. Oh, goodness, go back. So the Mn went from 7 to 2. It's been reduced. And then both of the oxygens actually changed oxidation numbers. This oxygen at -2 went to 0, and this one at -1 went to 0. But since this oxygen is part of the compound that got reduced, really people refer to the peroxide. And so that's the one that's being oxidized. I'm not going to put that up there. So for this one, this is iodate. Charge is -1. Oxygen's -2. Iodine is 5. Inside here, oxygen -2. Nitrogen +2. Iodine 0. 5. And -2. Goodness, I wish it would stop doing that. +5 for the I to 0 means this has been reduced. +2 to +5 means this has been oxidized. Okay, down here you have a whole lot of things going on. Hydrogen's 1, the magnesium is 0, +2, +3, +1, -2. The oxygen is -2. Goodness, I don't know why it keeps doing that. I'm not forwarding the page. Inside the dichromate, you have to do the algebra, and it is +6. And if you look at it, the hydrogen doesn't change, so it's not oxidized or reduced. Chromium goes from 6 to 3. It's been reduced. Oxygen is -2 to -2, hasn't changed. Magnesium has been oxidized. You will always only have one thing oxidized and one thing reduced. You will never have, on the left side of the arrow, 2 things oxidized, 1 thing reduced, or 2 things reduced and nothing oxidized. You have to have something lose electrons before something else can gain them. Okay, and so it's not always, you know, if this is reduced, that's been oxidized, because sometimes you'll have 3 things, but only one thing will be oxidized and only one thing will be reduced.